We move on to section 3.5. Now you'll recall when we were in chapter 1, we actually did some work in section 3.5 where we worked on some limits and finding horizontal asymptotes. And what we want to do here is we want to incorporate the idea of using horizontal asymptotes in order to help me create a graph. So horizontal asymptotes. A quick recall of how to find horizontal asymptotes. I take the limit as x approaches infinity of my function in order to come up with horizontal asymptotes. Also remember, quick little star there, if we've got a square root or an absolute value in the problem, we need to check the limit as x approaches negative infinity of my function also. Now, what that we also hopefully will recall from looking at when we're doing those limits is at infinity or a negative infinity, that the only difference between the red and the green, as I have it written, is that one is a change in sign. So here's my function. I got all kinds of crazy stuff going on here. So horizontal asymptotes to help create a graph. So let's find horizontal asymptotes of this function first. So I'm going to start out, in order to come up with my horizontal asymptotes, let's do the limit as x approaches infinity. So if I do that, here's an x in the numerator and a square root of x squared minus 4 in the denominator. The idea would be we're going to pick the highest power in the denominator, which in this case would be x squared, but it's underneath the square root. We're going to multiply the top and the bottom by something equivalent, which in this case would be 1 over x and 1 over the square root of x squared. And if we do that, our numerator is going to become a 1. Denominator is going to become the square root of a 1 minus a 4 over an x squared. So what do I find out? That limit is going to end up to be a 1 on the top and a 1 on the bottom. So what did I just find? I just found a horizontal asymptote at y equals 1. Now, it also says, because we have a square root in the problem, we're also going to have to include the limit as x approaches negative infinity. So if I multiply this time, what's going to be different? Well, the only difference this time is instead of multiplying, the highest power on the bottom is still x squared, and it's still underneath the square root. But now in order to make it equivalent, I need to throw a negative in on one of those quantities, because a negative number, like negative infinity, if you throw it in that bottom quantity, that bottom blue quantity I created, negative number squared, square root of all that, is going to end up positive. Whereas if I throw it in here, 1 over x is going to be a negative number until I change its sign. So in order for those two things to be equivalent, I need this extra little negative sign right here, and what that effectively does is that just means that this limit is going to turn out to be negative 1 instead of positive 1. So what did I just find? We just found out that we've got horizontal asymptotes at y equals plus and minus 1. So if we come over to our graph and say, all right, let's put a horizontal asymptote right there, and let's put another one down here. And remember, as my x's get really, really large, we're going to have to head toward this y equals 1 value from one side or the other. And as my x's get really, really small, I'm going to have to head toward this one down here. So just kind of keep that in mind as we're looking at our graph. Now we're supposed to do extreme and points of inflection and all the intervals of concavity. So this time, let's work our way through that. So I'm going to need some derivatives. I'm going to need a lot of crazy stuff. This is where it's going to get ugly, and it's going to hurt a little bit. So that x over square root of x squared minus 4, the first thing I might suggest to everybody as you're trying to figure out how to do this, let's change the function. This is my original function. X times x squared minus 4 to the negative 1/2 power. I would suggest every chance you get that you treat it that way. So now let's do our first derivative. So my first derivative is going to be pink, f prime of x. Maybe it won't be if I can't make that work. So f prime of x. First, derivative of second, negative 1/2. Quantity x squared minus 4, negative 3/2 times the 2x. Plus my second, x squared minus 4 to the negative 1/2 times the derivative of my first, which is a 1. So there's two terms in this derivative. If there's two terms in this derivative, let's clean them up. Let's make them look the way they're supposed to. So this first term is a fraction. It has an x squared minus 4 to the 3 halves in its denominator. In its numerator, let's see, those 2's cancel. There's a negative and an x squared. Plus, the second term has a fraction. And on the bottom of it, there is an x squared minus 4 to the 1/2. And the numerator, you already see the 1 that I put up there. Pardon me. So now, putting those two things together so I can come up with critical numbers and all that fun stuff, looks like I'm missing a common denominator. Common denominator would be x squared minus 4 to the 3 halves. I'm going to need an x squared minus 4 to the 2 halves extra in each side of that, or each part of that fraction. Clean it all up. How about, let's see, negative x squared plus x squared minus 4 over the top of an x squared minus 4 to the 3 halves. And if we do that, I think our first derivative is going to end up being negative 4 over x squared minus 4 to the 3 halves. So what are we going to know about this? Well, let's see. Critical numbers. Well, critical numbers, let's see. From my numerator, I'll have none. From my denominator, I'll get x equals plus and minus 2. But you know what we forgot to do in the beginning of this problem? We should have looked at vertical asymptotes while we were at it. So if we come back up and look at this thing, I guess I've got a little bit of space over here that I can do this. Where do we have vertical asymptotes? Well, this thing will be discontinuous. Oh, let's see. You know, if you take a number like 0 and you plug it in that original function into this y, you get a 0 on the top, and on the bottom you get a negative number underneath that square root. And if I wanted to find vertical asymptotes, I'd set that x squared minus 4 equal to 0, and I'd get x equals plus or minus 2. But here's what's interesting. I can't have y values. I will have no y values for anything in between negative 2 and 2. So while I have asymptotes, I'll have vertical asymptotes here at plus and minus 2. This thing also is discontinuous between x equals negative 2 and x equals 2. So in the middle of this graph, if we come over and we look at this graph, let's put some vertical asymptotes on it. I know I'm going to have a vertical asymptote at x equals negative 2. I know I'm going to have another one at x equals positive 2. But in between those two orange asymptotes, according to what we just figured out, there's not going to be any function. There's not going to be anything there. So the only thing we've got like a little tic-tac-toe board going on here. And I'm not going to have anything going on in between those two orange lines. All right, so back to our first derivative. So back to my first derivative. So if I look at this now, let's zoom back in a little bit, make it a little easier to write. So when I go and I look at what I've got going this time, so I only have critical numbers at x equals plus and minus 2. So if I set up my intervals, negative infinity, actually, let's do it over here on the side. So negative infinity to negative 2, negative 2 to 2, 2 to infinity. And remember, according to what we found a second ago, there's not going to be anything going on in this interval, but I still have to check what's happening around there. This time I'm going to take my critical values, I'm going to plug them into my f prime. They're going to tell me about my original function, and we're looking for extremas. So if I take my f prime, take a number like negative 5, top's going to be negative no matter what. Bottom, negative 5 squared is bigger than 4. That's going to be a positive on the bottom. Looks like we're going to have a negative result, which means my original function is going to be decreasing in that interval. Take a number like 5, plug it in. I think you're going to get the exact same thing we did when we plugged in negative 5, which means my function is still decreasing. Did we find any extrema? Nope, we have no extrema. All right, well, what do we do with this other mess then? So now I got to find the second derivative. Oh man, this has been so painful already. So when I go to find the second derivative, before I go on, how about if we change this to negative 4 times the quantity x squared minus 4 to the negative 3 halves. So now when I go to find my second derivative, which I guess I've been historically doing in blue, let's just do a straight chain rule. Negative 3 halves times negative 4, I think would be a positive 6, x squared minus 4 to the negative 5 halves power, and then multiply that by a 2x. So how about a 12x over an x squared minus 4 raised to the 5/2. And if we look at our critical numbers again, critical number at x equals 0. And in critical numbers, crit at x equals plus and minus 2. So this time if we go and do our intervals, so this time our intervals, again, negative infinity to negative 2, negative 2 to 0, 0 to 2, 2 to infinity. And I hope that you're ahead of me and you've already picked up on the fact that in orange up here we said nothing could be going on in there. So we're not going to have any potential inflection points this time because we have vertical asymptotes at both negative 2 and 2. We're plugging in this time into the second derivative to tell us again about the original function. So my second derivative, let's see, if I plug in 0, I'm going to get, if I plug in a negative number like negative 5 squared is bigger than 4, positive on the bottom, negative on the top, negative. Function's going to be concave down. If I plug in a number like positive 5, positive on the top, positive on the bottom, positive, function's going to be concave up. We have no inflection points because there's not a change that's happening there. And we have vertical asymptotes at negative 2 and positive 2. So we got to make all this fit. So if I want to make all this fit, come up here and look at our graph. So we have asymptotes all over the place, playing tic-tac-toe. We have no inflection points, but it's supposed to be concave down to the left of that first vertical asymptote. We have, and the function's also supposed to be decreasing. What will that look like? Concave down, it's got to get close to this green thing, concave down and decreasing. And on the other side of it, it's got to be concave up. The other side of this right asymptote, it's got to be concave up and decreasing. Concave up and decreasing. And we know it's got to get close to this asymptote. We did all of that to come up with that crazy graph.